Okay, woo. Yeah. So we're going to have alpha D-glucose. Alpha has the hydroxyl group down at the anomeric hemiacetal carbon, bichiral carbon. So glucose is down, up. Galactose would be down, up, this way. Fructose is going to be a 5-membered ring, but it's still six carbon sugar. 1, 2, 3, 4, 5, 6 carbon sugar. So when I bring together fructose and glucose, and I do a dehydration reaction between these carbon, this carbon and this carbon here, you can see that if I circle this, I've lost water. Okay? So water comes off again, and I'm going to form a special type of a bond. Now, in this case, this is a little bit different than what we've seen with the alpha-1,4 and the alpha-1,6. This bond here, that we make, this glycosidic bond here, is a special bond. It's a little bit different than what, than what we've seen up to this point. Because, so once you draw that, listen to this. Before, I don't have to tell the person that I'm describing the disaccharide to whether this hydroxyl group is up or down. Why is that? It's galactose. If it's up, it's galactose. If it's down, it's glucose. That is good. That is not an anomeric carbon. That carbon does not open and close. This is an anomeric carbon. That means it can go down or up. This is an anomeric carbon, meaning it can go down or up. Okay? This is a ketal. This is an acetal. So here's what happens. Because of that, I have to tell what anomer I have for these sugars. So this is an alpha 1 beta 1 glycosidic bond. Beta 2. It's a fructose. Glycosidic bond. Okay, does that make sense? Because I'm bringing together two anomeric carbons. That's an anomeric carbon. That's an anomeric carbon. I have to describe what anomer makes that disaccharide. And in this case, it's alpha 1, because this is down, alpha 1 beta, because this one's up, and it's carbon 2, this is carbon 1. 1, 2, 3, 4, 5, 6, okay? So this is an alpha 1 beta 2 glycosidic bond. Okay? So this makes sucrose. Sucrose is actually not really good for us. It's table sugar. Tablespoon of sucrose in your system suppresses your immune system for about 20 minutes while your body processes. That's not made to have that bolus of raw sugar. It is not good for it. And one of the things that we should really work on is eliminating raw sugar in our diet, because it is not healthy for us. But we are addicted to it, so, because it tastes good. My kids love it. They love Halloween, right? You know, an entire orange container full of that stuff. So just note that this is probably not one of the best sources of sweet that we should be putting into our system. Okay, we're going to end this with kind of a fun thing. I actually really like this. There are 4 sugars and 4 blood types. Okay, so if I draw galactose, you should know what galactose is. Okay, I'm going to do all these beta. Okay, so here's a D beta D galactose. I have the beta form drawn. Here's a different kind of a weird sugar. It's one of those that L-fucose. Okay, I'm going to call this G, and I'm going to call this F. So fucose is kind of a weird one, and the reasons why it's L, it actually tilts to the right. It has to do with this being a hydrogen here. Okay, so it's just one of those. It's still a right-handed, but it's left-handed because of the way this thing comes together. It's just one of those funny things with that 6 carbon being a methyl group instead of being a CH2OH. Okay, so it's just one of the little things. But fucose is one of the sugars that's in blood. The next two are kind of cool. They're subsets of sugars that we've already seen, but they have a slightly different makeup. So if I put a nitrogen down here, okay, if we haven't gotten to this functional group, we will. It's called an amide. I just messed that up. So this is called N-acetyl glucosamine. Okay. So it's glucose, but instead of having a hydroxyl group down here, like this one here, okay, it has an N-acetyl group. And again, you'll learn this functional group in the next chapter. It's called an amide, very important functional group. We build all of our all our proteins and enzymes using the amide bond. So it's a very important bond, and this is where we first see it. Okay, so that's N-acetylglutamine. We're going to abbreviate that. Right today. Okay. And the last one is actually just like this, but it's galactose, galactosamine. So it's going to be galactose, same form. Okay, so again, I'm going to do these all in beta just to keep them all the same. So this is also an acetyl group here. Okay. But in this case, this is N-acetyl galactosamine. And we'll call that AGA. Okay? So those are the 4 sugars that are involved in identifying blood types, which is, to me, pretty fascinating. And so here's the way this works. So if you're an O type, or if you're an A type, or if you're a B type, or if you're the rare AB type, what happens with this is on the blood cell itself, okay, off of that, all blood types, right off the blood cell have the AGL. Okay, so they all have this. Off of the AGL, they all have galactose. Okay, so galactose. All of them off of galactose have fucose. Okay, so all blood types have that moiety. If it's only these 3, though, it is an O type. Okay, so O, that's the universal blood donor, right? O type blood. Most people, that is the dominant blood type. So that is the dominant blood. The next one is A, and like I said, they all have the same 3 carbohydrates that O have. So we're going to have AGL, we're going to have G, we're going to have fucose. But here, for the A type, we're going to have an AGA coming off here. Okay, so you can see how it's different. So for A type, and this is A type blood. So A type blood takes one of these and branches it off the galactose. Okay, so that's A type. B type also is the same backbone as O, but in this case, okay, so we're gonna have AGL, we're gonna have G, we're gonna have F, but for B, you put another galactose here. Okay, so this is B-type blood. So those are your three blood types, and our body recognizes those or other bloods by the carbohydrates, the sugars that are on the blood cells themselves. So in our population, it's roughly 43% of people have O-type, roughly 40% of people have A-type, roughly 12% of people have B-type, and the AB is a mixture of these, and the rare one, and roughly about 5% of people are AB or the rare type. Okay, anybody know the blood type in here? What are you? Anybody? Is anybody AB? You're AB? Anybody else AB in here? I don't know my type. How many O that you know? Yeah, lots of O's. Yeah, how many A's? Okay, B's? Yeah, and then AB, only one AB, that's cool. Okay, so you can see that ratio, but what's going on there is literally the chemistry of it, I think, is pretty fascinating, because we're simply dealing with literally the combination of 4 different sugars to make up the 4 different blood types. So it's kind of cool. Any questions on that? Vampires like A, by the way. Okay. No, we're good? Okay, so that's it for chapter 15. We're moving on down the road. Chapter 16. What's that? Nope. Okay. Okay, so our new functional groups: carboxylic acid, carboxylic acid, carboxylic acid. We're going to talk about carboxylic acids and esters. Okay, so carboxylic acids and esters. Carboxylic acids and esters are 2 really cool functional groups. Carboxylic acids are all through medicine. All through medicine. We'll get into kind of the cool part of this. You've already seen the carboxylic acid. It is the R-carbonyl hydroxyl group. This is a carboxylic acid. Okay, that's a carboxylic acid. So it has a carbonyl. And it has a hydroxyl group. Okay, that's what makes the carboxylic acid. Esters are different. Esters are R-carbonyl, but instead of a hydroxyl group, they have another carbon out there. Okay. Esters are, hopefully Dr. Nagals does the ester lab with you when you learn their beautiful aromas of esters. It's where apples get their aroma, pineapples, oranges, bananas, banana oil. All those real fruity flavors come from esters. They have a real pleasant aroma. And it's fun to work with those because you can make them very easily in the lab. So, that said, this is the ester. First place we're going to start with the ester and the carboxylic acid. We'll start with carboxylic acids and we'll move into esters. We're going to start with their nomenclature. Okay, so how do we name these things? Well, in nomenclature world, carboxylic acids are the number one, the top, the highest priority of all molecules. Okay, carboxylic acids are the reigning champion. And the reason for that is that this carbon is the most oxidized under carboxylic acid conditions. Your next oxidation state for this is carbon dioxide, which is fully oxidized. So that's why oxidation state, that takes precedent. How do we name these? Well, if I take something like this, the most simple carboxylic acid, This is formic acid. Common name is formic acid. Okay, but its actual IUPAC name is methane or methanoic acid. So you can see that for the carboxylic acid, I'm going to add oic acid. Okay, that's the new thing. I take off the E and I put oic acid for carboxylic acid. So methanoic acid, ethanoic acid, propanoic acid. Formic acid happens to be the component that if you've ever been bit by a fire ant that they inject into you. Okay, that's what makes it sting when they bite. Acetic acid, one of my favorite acids. Here, this is acetic acid, or ethanoic acid is vinegar, right? Household vinegar has about 5% acetic acid in water. Really nice acid to have around the house for cleaning. Cleans floors really nicely, cleans glass really nicely, cleans countertops. It's a really nice solvent to use for cleaning. Breaks down calcium deposits and soap scum and things like that. So it's a really nice one to have around the house and use quite a bit. Okay, and so you can see how this kind of builds. This is ethane, but because it's a carboxylic acid, it becomes oic acid, so ethanoic acid. Okay, so if I were to name something like this, now that we go back to stick structures, this has 4 carbons on it. So 1, 2, 3, 4. So that is butanoic acid. Okay, if I put a methyl on it somewhere, this is carbon 1, 2, 3, 4. So that's going to be 2-methylbutanoic acid. Again, it just builds on what we already have talked about throughout the semester. Okay? Good? Okay. Physical properties of carboxylic acids. Super cool. Physical properties of carboxylic acids are that they are the most soluble of all organic molecules. Okay, they're incredibly water soluble. They really like water. They can solubilize up to 5 carbons, even 6, slightly soluble, whereas the hydroxyl group can only do 4. So they really do like water. So here's what happens with the carboxylic acid. Carboxylic acids have this very special feature. And that special feature looks like this. Okay. Carboxylic acids are the world champion hydrogen bonder. All right, they hydrogen bond. So if you think about this, there's an electron pair right here, and an electron pair right here. There's an electron pair right here, and an electron pair right here. So that hydrogen loves to mix with that electron pair. Okay, so they form what's called an intermolecular dimer. Okay, it's a unique property to only carboxylic acid. Some amides do that as well, but not as tight as the carboxylic acid. Carboxylic acid also, like I said, love water, and that's because they hydrogen bond to water as well. But they form these really powerful double bond or hydrogen bonds. Now, the reason why this makes them such one of the important things about them is you might remember this molecule. I don't know, some of you might remember it, some of you might not. But when we draw these molecules like this, these bioorganic molecules, you know, within the body you have these massive molecules, and one of them that I just find fascinating because of the chemistry of it has to do with the carboxylic acid. So this is an important biomolecule within the body, and when you look at this molecule, and again, I've mentioned this before, I've had this conversation, so it's okay for you to see it a second time. I'm okay with that. because now we see the functional group. What you have up here is a carboxylic acid, all right? So this is a carboxylic acid, and it has another one over here, and this is remarkable to me in that this molecule can form, this molecule can form an intramolecular dimer. Now this is so fascinating. This is called bilirubin 9 alpha. Okay, so this is bilirubin 9 alpha. And the 9 alpha comes from the fact that when heme is broken up, it's ripped out of carbon 9. So that's where the name comes from. So with this, here's why I'm drawing this, because bilirubin has this CH2 right here. These are sigma bonds, so they can flop around, they rotate. These are rigid. These are rigid paddles because they're all double bonds. Okay? And you can see that there. So it's like these paddles that do this. So what bilirubin does is it doesn't sit like I've got it drawn. It actually comes in and folds in on itself. And that's the power, and that's the beauty, and that's the frustration all in one of bilirubin. So if you look at bilirubin from that perspective, you end up with a really fascinating, you end up with a really fascinating system of hydrogen bonding. Again, hydrogen bonding is one of the hallmarks of carboxylic acids. So with bilirubin, what happens is you form this very dominant intramolecular hydrogen bonded structure, all right? So when I draw the rest of bilirubin in, okay? So there's bilirubin. Now watch what happens with it. This to me is what makes it so fascinating, and the carboxylic acid, now that we're responsible for the carboxylic acid. Notice, this carboxylic acid is a propanoic acid, so propane, 1, 2, 3, 1, 2, 3, propanoic acid. So this carboxylic acid up here comes over and bonds to this one. This carboxylic acid crosses over and bonds to this one. So when I draw that, and I'll exaggerate it a little bit here, I'm going to give myself enough methyl there. So with that, you can see what's happening, okay? And down over here, same thing. Okay, so watch. This carboxylic acid hydrogen bonds to both of these, the pyrrole and the lactone, okay? This one, hydrogen bonds just to, the lactam. Over here, that one hydrogen bonds to the lactam. This one hydrogen bonds to the pyrrole, okay? So here's the thing with this. Here's what's so, I think, so fascinating about the chemistry and science behind this. This is the reason that bilirubin is so toxic to the brain. This molecule here, even though when you look at bilirubin this way, you think this is very polar molecule. It's got carboxylic acids, which love water, pyrroles like water, lactams like water, so it should be soluble in water, but it's not. Bilirubin is insoluble in water. So what happens is it crosses the blood-brain barrier and causes brain damage. So the reason for that is explained here, because what happens is bilirubin doesn't have all that polarity out there flopping around for the water. It actually folds itself in on itself, and it cloaks all of its polarity, and what our body sees is this big layer of grease. Okay, so that's why it's insoluble in water, and it crosses the blood-brain barrier. Now here's what's really cool. You might know that alkenes are either cis or trans. Remember back to alkenes? Watch this here. This bond right here, if you look at it, okay, if we go here, cut it in half, ask ourselves the question, this carbon has a carbon and a hydrogen, that has a higher priority. This carbon has a nitrogen and a carbon, nitrogen's bigger. So this actually is a cis form of this, or we call this a Z. So this is a Z alkene here, all right? These alkenes here are ZZ. Here's what's so crazy cool. just like with cis and trans retinal in the eye, which allows photons to come in and it flips, when blue light comes in and it hits this double bond, it takes the Z and it flips it to an E, just like our eyes. And so that breaks up this hydrogen bonding, so the carboxylic acid can go find water, the lactam can go find water, and it becomes soluble. And that's why a nurse found this in the late 50s, that the infants that were next to the windows in the neonatal wards were going home sooner. And the reason for that is that the light is transferring this from Z to E, transferring this from Z to E, and then it's able to be gotten rid of. And I think that's just fascinating. Again, that's a review. I've already described that to you, but now you're seeing why it is with the carboxylic acid. You can see that the carboxylic acid is an amazing hydrogen bonder, and that's the important part. Okay? So one of the features of a carboxylic acid is the fact that it forms these really crazy tight hydrogen bonds. Okay? Any questions on that? Yes?
It's not a question on that, just could we move the tripod for that other?
This guy here? Yeah.
Over
The one I don't use?
for rewatching purposes?
Yep. Get rid of that guy.
Thank you.
Yeah, bet. Okay, let's talk a little bit about their chemistry, because that's always the fun part, right? That's what we're here for. We're here to learn the chemistry. So let's learn.
Dr. Anselm, we have another question.
Oh yeah.
Bilirubin is a derivative of hemoglobin, correct?
You want to see that? It's a derivative of heme. So watch this. This is, since you asked, and I love what happens with this. And this is really important, because when you look at this, well, yeah, I'm gonna go ahead and draw heme. Watch what happens with this. Okay, so if you draw heme, okay, so heme is this. Okay, so here's heme. And I love these types of questions, because again, it's the chemistry and the biochemistry that are so fascinating, which is why we're learning this. Okay, so this is heme. So heme actually sits in hemoglobin, right? Hemoglobin is the protein that we will see in a few weeks. Heme is the protein, or hemoglobin is the protein. This is the ancillary molecule that sits in the hemoglobin. Each hemoglobin has 4 of these that's bound to it. It's the iron here that coordinates with oxygen. So out here, oxygen sits connected to the iron. Or carbon dioxide, depending on which direction the blood's going. Is it coming in or is it going out? When it's coming in, it grabs oxygen, takes it to the cell, grabs carbon dioxide, and removes, and then the whole cycle repeats. And that's why this thing's planar, it's very flat. It actually flexes depending on its carbon dioxide or oxygen, changing its color. Okay, so with that, these are then used to attach to the hemoglobin. Isn't that kind of cool? That's how they actually attach, that's why they're up there. So, and the color of this, because this is all conjugated, and we won't talk about conjugation, but it's actually what we call an aromatic conjugated system. And because of that, when photons come into it, they resonate at the red frequency, which is why blood is red, okay?
So is that technically the reason that blood is blue in the body and it doesn't become red or visible to us until you actually bleed?
Bleed and it oxidizes. You got it. It's the flex. It's the flex, that slight flex in its planarity, okay? So here's what happens when the cell is damaged. When you get the bruise, or when the blood seeps out where it doesn't belong. What happens is the very first thing enzymatically is our body recycles the iron, so the iron goes away. But what else goes away is this carbon, okay? That carbon goes bye-bye. And so what happens is you see that you get 2 oxygens down here. All right? This is called, notice, it's an SH, there's a double bond right here. This is called biliverdin. Biliverdin is what color do you think?
Green.
Probably verdin, probably it's also verde, it's green, all right? It's green, and this then gets one more enzyme actually converts this up here to the CH2, which this is yellow, because this chromophore right here is yellow. This chromophore here is green. When it was completely attached, it was red. And that's why on a good bruise, you do see the dark, kind of the blue-purple, the bluish bruise, which is what colored blood is, and then it goes to the green, and then outside that bruise, it's yellow. And so you actually see all of the enzymes breaking down the original heme to the biliverdin to the bilirubin, and finally bilirubin is gotten rid of by putting a big giant sugar, glucuronic acids right up here. Isn't that kind of cool? So, yeah, I mean, it's just, this is all, carbon chemistry and biochemistry, really. But I think it's pretty fascinating. So thanks for asking that question, because it's fun to geek out a little bit more than just, there's a carboxylic acid. Yeah, biliverdin. Okay, let's talk about some of the chemistry of carboxylic acids. Carboxylic acids are all through medicine. They're all through medicine. They're all through our life. That's a very, like I said, very water-soluble functional group. It's an acid. The very first thing that you need to know are carboxylic. This is going to be a little bit kind of funny. Carboxylic acids are, guess what? Acids. Okay? I just put that out there because that's their most important property, is that they are acids. All right? So being an acid, if I take a carboxylic acid, if I take a carboxylic acid and react it with water, okay, or put it in water, one of the things that can happen is water can say, hey, I'm water. I can be either an acid or a base. I'm amphoteric. So if you put me in with an acid, this goes back to chapter 10, if you put me in with an acid, I'm going to become a base. So what happens is water comes over, grabs that hydrogen, and the electrons that were between this oxygen and the hydrogen, remember, a line is just 2 electrons. So the electrons then go onto oxygen. And so according to Le Chatelier's principle, it's actually equilibrium is to our left. You end up with this plus. Okay? So we are an acid-base reaction. So my acid becomes my conjugate base. My base becomes the conjugate acid. Okay? And that process is in a dynamic equilibrium. The equilibrium in this case is far, 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 far to the left. All right? And that's because acetic acid or any kind of carboxylic acid is not a strong acid. Remember what a strong acid is. What is a strong acid? It completely, dissociates in water 100%. Got it. Okay? It falls apart 100% in water. All right? So carboxylic acids are weak acids, meaning that when you add them to water, they don't disassociate completely. In fact, they have actually a pretty low Ka, which is the expression of how much these things disassociate. However, if you add a carboxylic acid to a base, an actual base, watch what happens. They are acidic enough to form salt and water. So with that, if I take a carboxylic acid, and react it with a strong base, okay? Notice over here, I'm just reacting it with water. Here, I'm reacting it with sodium hydroxide, which we know is a strong base, because we learned our strong bases, our 7 strong bases. So what happens in this reaction is it's not an equilibrium reaction. It goes only one direction. And what I get out is the salt of the acid and the base plus water, okay? So this is a neutralization reaction. It's not an equilibrium reaction. This is an equilibrium reaction where you have an acid base, conjugate base equilibrium. This is an acid base neutralization where you actually get out a salt and water, okay? So if I took a specific carboxylic acid, like one that you memorized, benzoic acid, if I took benzoic acid and reacted it with sodium hydroxide, I'm going to get an acid-base reaction to form a salt and water. So with that, you get out benzoic. Okay, so here's what happens. I'm going to have a base-acid reaction. Base here attacks the hydrogen. These 2 electrons then go on to the oxygen, okay? It already had 2 pairs, so those go back on, so it gets all of its electrons, which is all of those electrons here. Sodium goes to water, okay? And you can see that oxygen still has its electrons. All right, so I went from an acid and a base, or a base-acid reaction, to a salt and water. Down here, the byproduct, of course, is still going to be water. But with this, I went from benzoic acid to sodium benzoate. Now, we'll talk about nomenclature of esters here in a second, and that'll make more sense how I named them. Has anybody heard of sodium benzoate? Okay. No? You've all eaten it in the last 24 hours. So sodium benzoate, again, when you remember our circle of life and our death row, remember that circle of life when you go into Winco, when you go into Albertsons, circle of life, it's all the HVAC, so all the stuff that's the milk, the dairy, the poultry, the produce, you know, everything that has to have refrigeration is typically around the circle of life, right? Oftentimes, there's a freezer row that's closer to circle of life, but down the middle aisles is death row. And the death row comes from the fact that it's all dead. And one of the ways that they actually preserve it and keep it dead is to put sodium benzoate in it. So the next time you go down the aisle, pull up a can or pull up a cup noodles, it's not cup of noodles, it's cup noodles, pull that up and look at the ingredients, and one of the very last ingredients you'll see is sodium benzoate. It's something that preserves. Okay, it's an actual toxin. The thing is, we're just a large organism, so we can handle a little bit without it hurting us, but it kills microorganisms and keeps it from spoiling. Okay, so you'll see lots of sodium benzoate in the cans and the green beans and things like that to keep it from spoiling. So that salt there becomes kind of useful because we actually use it in preserving foodstuffs. All right, now that brings us to esters. Esters are really neat molecules. So esters are this functional group. Okay. Esters do not have an H, it's just ester without the H, and I think I've already explained why that is. It's because they don't have the Holy Spirit. So esters have this general layout. And with that general layout, there's something very important with esters. Okay, so I know we've got like 7 minutes left, so stay with me on this. I'm going to go to stick structure because I want us to switch over to stick as soon as possible. Okay, so that is an ester. All right, what kind of ester is it? So here's what we need to do. We need to make a distinction between the carbon chain coming off the oxygen and the carbon chain that the carbonyl sits on. So we need to make a distinction between the carbon chain coming off the oxygen and the carbon chain that contains the carbonyl. So the way I do that is take a pen and cut this thing right through that bond. Okay? Because it's the carbonyl side, or the carbonyl chain, which becomes the parent name. And that should make sense. This carbon has a higher priority than this carbon. Okay, so that should make sense. So when I circle it, this is my base name. Okay, so just like before, it's not butane, it's butane, but we say O8. So our new word is O8. All right? So it's not butanoic acid, not butene, not butanal, not butanone, not butanol, but butanoate. But I'm still not done. What kind of a butanoate is it? Oh, well, that's when I go to the other side of the blue line and I ask myself, how many carbons are coming off of the oxygen? How many? 2. So that becomes ethyl with a space, it's 2 words, ethyl butanoate. Okay? So try this one. Try to name that one. See what you get. Okay, so what am I going to do with this blue pen? You got it. I'm going to cut this thing in half. I'm going to cut it through the carbonyl and the oxygen, just like I did over here. What side contains the carbonyl, right side or left side? So that's my parent. So how many carbons are circled in that? 3. So what do I call that? Propanoate. Good. Propanoate. What kind of propanoate is it? Well, I come over here and I circle the carbons off the oxygen. That's 1, 2, 3, 4, 5. So what do I call that? Pentyl propanoate. Good, good. Which, if you want to crash the plane or land the plane, look over here. That's where the name comes from. What kind of benzoate do I have? Oh, I have a sodium benzoate. What kind of a benzoate do I have if I do this? What's that benzoate? Butyl benzoate. Yeah. Again, cut it in half. This is your special. What kind of special is it? Oh, it's a butyl benzoate. Cut it in half. Benzoate. What kind of benzoate? Oh, it's a sodium benzoate. Okay? So again, nomenclature in organic chemistry is very systematic. Hopefully, we're tracking along. So we only have 2 functional groups to go in nomenclature. Amines and amides. We've got it. All right. So let's pick it up on Friday. We'll pick it up with chemistry of esters. Super fun. Super cool chemistry.